Okay, please pardon me for that. I had to leave the meeting because the PDF wasn't opening. So yeah. Uh, yeah. Please confirm with me so that we start. Is the screen visible and my audio clear as well? Please confirm with me. Give me a thumbs up. I think we're behind schedule. All right. I had to leave the meeting, so sorry. Please confirm with me, is my screen visible and my audio clear as well? Only one can see the screen and hear me. 2. Right, thank you. So question number 1 was about briefly discussing 4 abstract data structures. Briefly describe 4 abstract data structures. That's 4 marks. Okay, so we start with Danny. Would you please help us? First of all, just list them before discussing.
List them?
Yes.
Okay. The first one is Q.
Okay. 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 You can go beyond. You can go beyond that. There is also an array. Remember. Okay. Good. Okay. Now let us discuss them.
Okay.
Please go ahead.
So for Q, so it's more like
Okay. Good. Okay. 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 Non-linear. Non-linear. Yes. Okay. 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 Good. Okay. Uh, thank you. That's to the point. That's to the point. We're not getting anything away from that. So the solution has just been shared in the group. And these are some of the concepts that we discussed quite extensively. So there are lots of data structures that you can talk about. Are they linear? Are they non-linear? And so on and so forth. They didn't, remember, the question didn't say linear data structure. The question said data structures. Okay, you can combine these. If you want, you can stick to just the linear data structure or non-linear data structure or both. Basically, that is up to you. So this is what he was talking about. There's a list, there's a queue, there's a stack, there's tree, there's array, and so on and so forth. So a list, just basically just a linear data structure. Q is also a linear data structure. Why do we say a linear data structure? Because when you have items in a list, you put one after the other. That makes it linear. In a queue, you've been on a queue before, okay? Let's say in ShopRite, you've been on a till. You can't jump a person or skip a person that you found in line there. Okay, so this is also a linear data structure, but it uses a FIFO principle: first in, first out. So if you found 3 people on a queue before you, the person in front, that means the person arrived first. Okay, and that will be the person that's first in, and that will be the person that must be served first, and that is first out. Okay, stack is also linear, only that you put items on top of each other. That's stack. Okay, I think we've used this concept lots of times in our lives. I'm stuck, I don't know what to do. It's more like you know what to say, but there's just that trouble thought which is on top of what you really want to say. Okay, it can't be unstacked, so it can't be accessed no matter how hard you try. So the best we can explain that is in last in, first out. When you begin stacking your clothes, the cloth that is going to be on top, that will be the last in cloth, and it will be accessed first, that is first out. Okay, tree is a non-linear. We've seen a tree, okay, just like a tree in real world. It has all those branches, so we are not saying there is this line, there is this line. Things there are just haphazard. So it's a non-linear data structure holding a collection of data or items in hierarchy. Hierarchy, we mean from either top to the bottom or bottom to the top. That's what we are saying there. I hope that's clear. Yeah, thank you, Danny, for that. Kindly give me a thumbs up if that's clear. Okay, good. Let me let someone in. Okay, Kumbu, welcome. Right, so we just discussed the first question. Give me a break. What's happening? Okay. I think we've been together on this one combo on data structures there. So arrays, lists, queues, stack, trees, and so on and so forth. 2. Describe a scenario where bubble sort would be preferable over a quick sort. Describe a scenario where bubble sort would be preferable over a quick sort. Okay. Perfius? Think that's your question. Perfius?
So,
There's a question there. Would you please give a comment? Describe a scenario where bubble sort would be preferable over a quick sort. Remember Max there? Max there? Think we. Okay. You can even explain from the solution point of view, that's fine.
the first time I said that it's more evidence to say that people that
Okay, let me just explain what this means. Remember, the question is about a quick sort and a bubble sort. So why is a bubble sort a scenario where bubble sort is more preferable to a quick sort? Okay. Is there anything that I can use? Do we have some type of diagram? I hope we do. Okay, I will use this example. I will use this example here. I hope you guys can see it. Kindly give me a thumbs up. Can you see this diagram? Okay, good. So what we are basically saying is what quicksort behaves this way. Remember, wherever we are talking about tree traversal, we talk about three concepts there: the in order, the pre-order, and the post-order. And the term used for that is recursion. Recursion basically is a function that keeps calling or refer to itself. So that function keeps on calling itself. Okay. So we'll give an example. We will not mention the type of tree traversal that we're doing here, but I'm trying to demonstrate why bubble sort is of essence. So what we are saying is, in tree traversal, so we start with that one, we go to that, we go to D. Again, we come back to B. That's when we can go to E. Again, we come back to B. That's when we can go to A. We go to C. We go to F. If there is an element there, we go to that. Then we come back to this. That's when we can come back to that. We come here. That's when we can come here. Now, I want to focus you here. So 1, we go here 2, 2, we go here 3. We come back to this. That will be number 4. So 1, 2, 3, we come back to this 4, then we come here 5, then we come here 6. Okay, so the more we are doing this, the more memory we want for that, because we are saying, remember, all these are operations that we are performing. So from A to B, B to C, from A to B, B to D, D to B, B to E, E to B, all these are operations. Okay, again B to A, that's when we come here. Then we start A to C, C to F, F to that one to F, F to G, G to F, F to C, C to that one, then we come back to C, again we get back to A itself. Now, I'm sure you can agree with me, we are doing a lot of operations. It's like we are doing the same thing or making the same point repeatedly, which is not efficient. And that's what quicksort does. Okay, that's what this point is emphasizing. Okay, so so quicksort is needed when items are small. Remember, we kept going back and forth. These items are looking small to our eyes. Okay, where? Okay, these items are looking small to our eyes. But if at all we start keeping, we'll keep A first, we keep B, we keep D. If we just say whatever we visit, we keep. So we keep A, we keep B, we keep D, we come back to B, we keep B again, we come to E, we keep E, again we come to B, we keep B again. So you'd find that B will exist at least 3 times. We come back to A. A now appeared 2 times. We come to C, we keep that. E, we keep that. We keep this item. We come back to F, we keep it. G, we keep. Again, we come back to F, we keep it. So you find that, let me let someone in. Teresa, welcome. We are late.
Thank you.
We are late today. Why? Right. Okay. So you would find that we are keeping these items repeatedly. And the more items we keep, the more memory we want. We want for that. That's the reason. Let me just demonstrate again. So we keep each item. So first of all, we keep A here. We visit B. We keep B. We visit D. We keep D. Again, we come back to B because we can't go direct to E there. So we keep B again. Then we go to E. Okay. Again, we can't jump this side. We have to go back to B. Then we go back to A, which we started with. Then we go back to C. Then we go to F. Then we go to wherever this is, maybe K, for example. Then we come back to F, we keep it. Then we go back to G, we keep it. Then we go back to F, we keep it. Then we go back to C, we keep it. Then there is this guy here on the right, for example Z, we keep it. Again, we go back to C, we keep it. Then we go back to A, we keep it. These letters look very, very small, but we are doing this repeatedly. That is what recursion does. Okay, so it requires a lot of memory. Instead of us just keeping 1, 2, 3, 4, 5, 6, 7, 8 items, you would find that all 10 items, for example, we are going to keep 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 I've written here. Instead of 10 items, we have 7 more items in Access, and that will require us lots of memory. And that is what this point is trying to stress out. So bubble sort is required in when the memory is small. Quick sort has recursion. Okay, that recursion is not required because unlike bubble sort. Okay, so whenever we have small memory, a bubble sort is required. Okay, then bubble sort is required. That is point number 2. Bubble sort is required for nearly sorted or already sorted items. So the good example that we can use is again this A, B, D, E, C. This is not good. Okay, this is not good for bubble sort. DEB, again this is not good for bubble sort. DBE, again this is not good for bubble sort. Bubble sort, among these, we are going to look at for the list of items which are nearly sorted out. That's what we are going to go with. B comes before D, D comes before E, D comes after B. So we can't go with that. Okay, B must be first. Then we remain with A comes before B, B comes before D, D comes before E. In spite of we have C here, this is nearly sorted, because if we see DE, then BG, then FCA, this is not close to that. So bubble sort works well for nearly sorted or already sorted items. That's what that point is trying to stress out. Okay, that's what this point is trying to. So the data is almost or completely sorted. It's either almost sorted or completely sorted. And the memory is limited. Remember, the memory is small. Okay, for small items, we would just like to use the limited memory because items are small. That is, when less memory is needed, no recursion is needed. So when stable, sort is required. That is, when items keep the original order. That's what we are saying there. Is that understood? Kindly give me a thumbs up. Is that understood? If you have a question, please unmute yourself. Okay, good. Okay, question number 3. Why is it important to analyze algorithm? Why is it important to analyze algorithm? Why? I think this one will give it to we will give it to Teresa. Why is it important to analyze an algorithm? Don't worry, all of us are going to be pointed out. Just prepare. Please go ahead.
To discover the characteristics of
Okay.
or to find out the behavior of an algorithm in terms of the running time and the sensitive.
Okay. Okay. That's perfect. That's perfect. I don't know. Can you guys see my presentation? Oh, that's good. I don't know why I can't see it. Can't see it on my screen when I do this. So let me do this. Okay. Now I do this. Okay, that's better. Right. So wherever you just see these words, let me present this back. Do not get confused. Wherever they say algorithm analysis, algorithm, they're just talking about algorithm analysis. Okay, algorithm analysis, and those are the same reasons. So why is it important to analyze this algorithm? Okay, and we discussed this lots of times. Nonetheless, we just do this. Okay. So number 1, remember, I think we've given lots of scenarios. Given a problem, okay, all of us here, we're about 7 of us. So all of us here in this meeting, given the same problem to work out, and they would want to pick the person that is going to come out best. I think this is what happens even in the quiz. You are given these sets of questions. So if this one fails, go to this. This one fails, go to this. This one fails, go to this. Until one group state an answer. Otherwise, no group is rewarded. So, given a problem, you come up with an algorithm. Another one can come up with an algorithm. So those algorithms, basically we're just saying, we are going to discover the characteristic. A characteristic is basically the reason behind functionality. How is the design which is going to be responsible for that functionality or for that item to function? We'll give an example. If you talk about parabolic dish, you guys do have these top stars. You have this top stars dish. You have DSTV dish that's in parabola shape. You have a parabolic dish. What the design of that dish influences its functionality. Okay, the design influences functionality. That is quite important. So that's what we are saying. So we'll try to discover the characteristics. Okay, then we evaluate by comparing. So we're going to say, okay, you have this algorithm, you have this algorithm, you have this algorithm. Let us evaluate. Okay, uh, uh, let's compare so that we pick the best. That's one reason what she was trying to say. Then we are trying to find out the behavior. Then how are they going to behave? Okay, in terms of how much space are going to are they going to take? Of course, we wouldn't want an algorithm which is going to take the entire computer's memory. We wouldn't. How long will it take? This algorithm will say this algorithm will take 5 seconds, the other one 3 seconds, the other one 10 seconds. Of course, we want the faster result. That's what we are saying. So first mark there. Then this guy contains 2 marks in terms of running time and space, which makes it 3, and correctness. We wouldn't want to just pick an algorithm. We want to ensure that this algorithm is functional. That's quite important there. Are we good? Any question? The rest of us? Okay, thank you. Thank you. Okay, good. Question number 4. What criteria can be used to judge an algorithm? What criteria can be used to judge an algorithm? What criteria can be used to judge an algorithm? So this one goes to Wankumbu. Okay, good. Okay, in terms of, okay, good. Then simplicity. Thank you. Basically, we won't take anything away from you. That is very right. Okay, so we just present that. Okay, good. Okay, so correctness, or just correctness there. We want to ensure that this algorithm is correct. This algorithm is efficient, and we keep saying efficient, basically in terms of space it takes and time there. I think that is quite right. And simplicity. Your algorithm must be not that complex. I think that is quite important. Okay. Question 5. What steps are taken in experimental studies to analyze algorithm? What steps are taken in experimental studies to analyze algorithm? This one comes to the chamber. Okay. Okay. Yeah. Okay. Okay. That's right. Yeah, that's right. Very, very right. We won't take anything away from you. Um, Nothing is going to be taken away from you. Okay. So first thing first, you write an algorithm, then you run that algorithm, then you collect the actual time that is took for that to run, then you plot the graph, and this is what you were saying. Okay, first of all, you write that program, which you are going to use to implement that algorithm. So I think we've talked about these a lot. So write, run, then record there and plot the graph. Okay. Okay. I think nothing to explain much about that. Right. Okay. So list and describe uh, 4 asymptotic notations that are used in algorithm analysis. List and explain 4 asymptotic notations used in algorithm analysis. So let us start from Dan again. Let us start from Dan again. Yes, that's true. Just try and describe. Just try and mention them. Just try and mention them. I think that's quite important. Try and mention them. Okay, there are 2 that is well known. There are 2 that is well known. I think on that one we can't argue. No argument there. There are 2 that are well known. Which one and which one? Okay, so if you can mention the alpha and omega, those are even bit complex. I expected you to say big O and small O. Yes, that's what I meant. Yeah. So basically, basically we have big O, alpha, omega, and small. Very important. Then you begin putting that. I think we have discussed this extensively. Just this is the time to process that number of input, which will be equal to big O multiplied by the function. This is the function. So this function, the n represents either linear, quadratic, um, cubic, logarithmic, and so on. So this function can be linear, this function can be logarithmic, this function can be, and so on and so forth. So time which will be taken to process this number of input must be equal to big O multiplied by that function. Then that is a description. Okay, remember, in your description you just have to, in your big O, you just have to change here less than or equal to, just put that, then the big O is that constant. So if there is a positive C which we put there, and the starting point, which is n sub 0. Alpha, same thing, just know the symbol, just the alpha there, multiplied by the function. Okay, it's T of n, T of n, T of n everywhere. Just know the symbol. If it's small o, again this was an honest mistake, is f of n. Here it's function of n, just like here. Okay, omega, just it's more like a big O, but there is that, more like a bulb chain, more like that bulb filament. You just put it there. Okay, so in alpha, now this changes. Okay, and the C there. So if there is a positive C and the starting point, then the time, this just come back like that, then greater than or equal to, this symbol is replaced by C everywhere. This symbol is going to be replaced by, except for omega. Omega, you just have to know the alpha and big O. Those are two conditions for omega. Okay, those are two conditions. Small o, basically, when you know big O, the small o you just remove. You just remove the equal to there and leave less than. That's basically what we are saying. Are we good? Are we good? Okay, thank you. Please go ahead. No. Okay, let me put clarity to that. When they say, the question is list and describe. Okay, you are answering mathematically. So those asymptotic notations. So what we are basically saying, when you say, for example, you are listing, what is the list number one? Big O. What does big O looks like? Okay, and just a simple that, and this only comes in when the big O is replaced by C. Okay, and in fact, this statement here, I think I've said it before, this statement here has to come after this very guy. So you say, if from here, if there is a positive C, okay, and n O, okay, that is the starting point, n sub 0. Okay, so if there is, just like here, if there is a positive C, which is a constant, and n of 0, okay, you can say such that O, then, which was supposed to be here, this time it takes to process that is less than or equal to, just replace that by c, and everything else remains the same. Please try by all means not to complicate the process. I don't know whether I've answered your question or not. Okay, thank you. Please give me a thumbs up, otherwise unmute yourself and ask that question. Okay, thank you. Okay, good. Question 7. It's about true or false. And a very generous question. Based on orders of growth, state whether the following are false or true. A. 2n plus 10 is less than or equal to c of n. Remember, c is 3, n sub 0 is 10. So is the first guy true, whether, or false? Is the first guy either true or false? Am I mute? Okay, this one is directed to Namkale. This one, Namkale. Is A true or false? The first A, is A true or false? Is Namkale in the meeting? Okay.
True.
Okay, A is true. Would you please say why? They're just basic calculations. Beg your pardon? Yes, C is 3. N is 10. When you see N sub 0, this is just a starting point. It means wherever you have N, put 10. Wherever you have C, put 3, which makes that correct. What about B, Namkale? I think the whole question is for you. What about B? What about B? Is Namkala in the meeting?
Sure.
Okay, good. What about C? Okay, D? Okay, that's very, very, very correct. Let me just all of them were true. Okay, let me just overemphasize on D. Please, please, wherever you have big O, okay, think I have to present this back. I have to present this back. Okay, so for big O, for big O, for big O, the left hand side will never be greater than the left hand side, the right hand side. Never. This side, the left hand side, will never be greater than the right hand side. That's why it's less than. It can only be equal to. Okay? For small o, just like big O, the left hand side will never be greater than the right hand side. Always. That's quite important. That's quite important to establish. Okay, so if we go here now, you have seen the big O here. That means even when the number here is bigger than this, okay, if this number here is bigger than this will make the whole statement false. Okay, but if this number is smaller here, if this number is smaller, for example, let's do this. Let's do this. 1000, then there's n here. N is 10. So 1000 multiplied by 10, this will be 10,000. But this is 10. When you say 10 square, this will be 100. But because we're using big O, it is less than or equal to. As long as we have equal to here, this makes the whole statement true. Based on the big O notation that you've learned, it is less than or equal to. Even if this number here is less than or is bigger than what is on the right, but because we have used the big O, the equal sign makes the whole statement very, very accurate. Are we good there? Can you give me a thumbs up? Are we good there? Because someone can ask, no, but 1000 multiplied by 10, this is 10,000, and 10 square is 100. The key here is big O. That's the key. Very important. So these are simple tricks that we must be paying particular attention to. That's quite important. What are different types of graphs? We looked at graphs. What are different types of graphs? Teresa. Just be ready. I'm coming for you. Just strike on or at random. Okay, please go ahead. You are answering. Yes. Okay. 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 That's basically what that's very basically true. So all those are true there. So there's a directed graph. The question was what at different times. So just stating. Would you give a comment about the graphs that you've just mentioned? Would you please give a comment? Would you please give a comment? Okay. 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 That's perfect. That's very very perfect. So what she means for those of us, directed graph is basically when you have a node A here. Um, I think all of us know what a node is. So we have a node here called B and A, and we have a node here called B, and there is that line which connects them, which is an edge. So when we put an arrow from A to B, that makes it directed. So there's a direction, there's a pointing symbol. Unweighted or weighted, if at the same between A and B, we say okay, the distance between A and B is 10 kilometers. So there is a value attached to that line that makes it weighted. Unweighted or undirected, we just remove that arrow. Unweighted, we just remove that value. That's quite important to establish. Okay, we do this. That's question 9. That's question 9. Good afternoon, thank you. How are you? Good. Right. So, question 9. Briefly explain the concept of in-place sorting. Briefly explain the concept of in-place sorting. So this one goes to Wankumbu. In-place sorting. Okay. 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 Good. Basically, that is very very correct. We are not taking anything away from that. Okay, I'm happy with the progress that we are making. Basically, in-place sorting, we're just saying, uh, 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 it's just sorting in place. So we don't need sorting is putting elements in order. Okay, if at all we are in a room of 10 people, we don't have to say this room is too small for us. Maybe we like on a bus, for example. I hope I'm not offending people. Um, uh, uh, in a bus, for example, maybe minibus per se. Each row requires that 4 people sit there. Then there are 2 chubby people that have come in. Then there are also two slim people, thin people that comes in. So what we are saying is, please, because it's the same bus, let's just balance up things. So this one, since they are chubby, they go to that city, then that one comes here. We are trying to balance that. So no extra memory is needed. Okay, swapping elements are directly applied. Okay, imo jump hapo, you jump, come here, and so on and so forth. And those are examples. It is good for memory efficiency. Not like boy milika basi ntengereko hapa. We don't do that. That's what that means. Okay, that was number 9. That was section A, or 8th section. That was 8th section. Briefly, tree traversal, show that briefly binary works, and it can be okay. I think here we were quite limited in terms of we answered 1, then we answered 5. Okay, then we answered. Okay, right. So we do section B tomorrow. I think section A we are done. You guys should go and study. Are we together so far? Are we together so far? Okay, good. I have to clean the video and post it later. I will try by all means before midnight. You are free to sign out unless you have a question. Okay, good.